Okay, hello everyone. I welcome to all in our lecture series on laser physics. In this lecture series, we are discussing these topics, which are most essential for B.sc, B.Tech, M.sc, M.Tech, and various entrance examinations. In our previous classes, we discussed these topics with detailed note. These topics also. Last class we discussed this one: helium neon laser construction, its construction, working, and applications. In this class, we are going to discuss semiconductor diode laser, its construction, working, and applications. Okay, so let us start. In our last class in detail, we have been discussed about this helium neon laser system, its construction part, working, different transitions, and its applications. Okay, in this class, we are going to discuss semiconductor diode laser, which is a two-level laser system. If this question will be asked, it will be asked for 3 to 4 mark in your exam. Whatever we are going to discuss in this class, it is enough for full mark, for 3 to 4 mark. Okay, no need to write extra. This is enough. First, we are going to discuss the construction. See here, semiconductor diode laser is nothing but a PN junction. What is the construction here? It is specifically fabricated PN junction diode only. This diode emits laser light when it is forwarded biased. The laser diode is made up of two doped gallium arsenide layers. One doped gallium arsenide layer will be produce N-type semiconductor material, whereas another doped gallium indium layer will provide P-type semiconductor material. So this is the P-type semiconducting material, this is N-type semiconducting material, which is connected here, and this is the intrinsic active region, or the so-called barrier, PN junction. This is the PN junction. This side is highly reflecting, and this side is your partially reflecting, through which the light will be come out from this instrument, or your system, laser system. Okay, working principle. Here you can see P-type, N-type semiconductor. When joined together, we can form the depletion region or potential barrier. So here in P side, this is the ions, this is the negative ions, this is the positive ions, or this is the acceptor ions, this is the donor ions. How the PN junction formed, that we are not going to discuss over here. So this is the PN junction, or charge-free regions. Charge-free regions. When we are going to put the forward bias, that means positive terminal is connected with P side, negative terminal will be connected with N side, then here excess charge carriers electrons will be flow from this side to this side. Because this is negative, it will repel the excess negative charges towards the junction. As this is positive, these are the holes, this white color is the holes coming towards the, from this side towards the junction. So these electrons and holes, they are going to diffuse or recombine in this section, in this PN junction or depletion region. When they are going to recombine, when the positive ion or hole will be recombined with electron, it will provide energy in the form of light. And if those photons or light are uh, coherent or interfere constructively, then we can form the laser action. This is the simple principle in your simple semiconductor diode laser. Same thing it has been written here. You can see, when forward biased voltage is applied to diode, free electron starts moving from negative terminal, here this side terminal of the battery, to positive terminal of the battery. Similarly, holes starting from positive terminal of the battery to negative terminal of the battery, as shown in the figure. Across the junction, they are recombined with each other. Across this junction, they are going to recombine. Okay, during the recombination process, the light radiation is released from a certain specific direct band gap semiconductor like gallium arsenide. This light radiation known as the recombination radiation. So whenever a negative and positive will be recombined, a energy will be radiated. If the energy will be in the form of light or visible range, then we can say it is a the so-called light. If it is a heat, then it could not be visible. It will be in the infrared region or far infrared region, not to be visible, but energy will be released. In specified diode laser system, the energy whatever or the photon whatever will be released at the time of recombination, it will fall in the visible region, can be visible, or we can say the so-called light. And these photons, if they interfere constructively, see, many electrons and holes are going to recombine, and suppose one hole and one electron recombine and one photon created, and another one recombine, another photon came out. So if these two photons are interfere constructively, then we can found a coherent source, light coherent light source, that is the so-called laser. Okay, here the photon emitted during the recombination stimulates other electrons. See, whenever these photons will be recombined with each other, sorry, when these electron and holes will be recombined, a photon will be released. That photon will be stimulate other electrons and holes to recombine. As the result, stimulated emission takes place, which is produce a laser action. Okay, here you can easily understand with the help of band structure. This is p-type material, this is n-type material. Whenever we are going to put the forward bias, these are going to be recombined. These holes and electrons are recombined at the p-n junction. If we are going to consider the band structure, this is your conduction band, this is conduction band side, this is the valence band. So for the p-type material, excess holes we can found in the valence band, and in n-type material, excess electrons we can found in the conduction band automatically. This is the characteristics of n-type material, and this is the characteristics of p-type material. Having holes, large number of holes in valence band, in n-type material large number of electrons will be in the valence conduction band. So whenever we are going to put the forward bias, these electrons and holes are recombined at this junction. Okay, when they are going to recombine, a photon will be released, and this photon again ignite or stimulate these electrons and holes, that they have to recombine again and again, which will produce large number of photons in the form of coherent manner, and we can found the laser action. This is the simple principle. Same thing it has been written. Figure shows the energy level diagram of the semiconductor laser. When p-n junction is the forward bias with large applied voltage, the electrons and holes are injected into the junction. That means this one. In considerable concentrations, the region around the junction contains a large amount of electrons in the conduction and large amount of holes in the valence band. So at the junction, already large amount of holes valence band is we can found, and large number of electrons we can found in the conduction band at the junction. So when suppose one electron and hole pair recombine, whatever the energy will be released, that energy will stimulate other electrons, that it has to transit to the lower state, or we can say it will transit to the conduction band to valence band and recombine with holes, which will be which will eject another photon. Suppose one photon ignited this one, this ignited or stimulated this electron, and this electron recombine, another photon will be generated. And if this electron will be stimulated and recombined, another photon will be generated. So likewise, in a fraction of second, large number of photons will be generated due to this process, and all the photons will be interfered with each other constructively, due to which we can found laser action. Same thing that it has been written. Large amount of holes in the valence band, hence the conduction of a population inversion is achieved. Condition of a population inversion. So population inversion means large number of electrons here in the conduction band and large number of holes, or less number of electrons we can found in the valence band. So this is the population inversion condition. The electrons in the conduction band transit to valence band and then recombine with holes. When the electrons transit from conduction band to valence band, they radiate energy in the form of light equivalent to band gap of Eg. So when the electrons in conduction band will transit to valence band for the recombination process, it will radiate the energy in the form of light. How much will be the energy? Energy will be the this energy gap Eg, right? Right. When forward biased voltage is increased more and more, light photons are emitted, and the light production, here something uh, is written not to be visible. Wait. Yes. So here, light production instantly becomes stronger. So when forward bias, if I'm going to increase somewhat, then uh, more and more light photons are emitted, and light production instantaneously becomes stronger due to constructive interference. Constructive interference. These photons will trigger a chain of stimulated recombination, resulting in release of photons in phase. In phase means it is going to produce the constructive interference, provide which can provide, here language is somewhat, I'm going to correct it, in phase, okay, which gives out the laser beam of wavelength 8400 angstrom, right? 8400 angstrom. The wavelength of the light is given by this relation. It can be evaluated by this relation. Uh, Here h mu equal to Eg. Mu is nothing but c by lambda. So lambda equal to sc by Eg. So these are the characteristics of semiconductor diode. It is a solid state semiconductor laser. PN junction diode made from single crystal of gallium arsenide is used as active material. The direct conversion method is used for pumping action. Power output. The power output from this laser is around 1 milliwatt only. Nature of output. Nature of output is continuous wave nature. Wavelength around 8300 to 8500 angstrom. What are the applications? These are the applications widely used for fiber optic communication, used to heal the wounds by infrared radiation. It is also used as a painkiller, used in laser printer and CD writing and reading. Okay, thank you so much for watching this video. In our next class, we are going to discuss carbon dioxide laser. Okay. Okay.